In my shop, and in every engineering lab I've ever visited, safety is the first and last thing we think about. It's not just a checklist, it is a mindset. We often focus on the obvious dangers, the sharp end of a tool, the high voltage of a power supply, the sheer mass of a moving machine. But some of the most critical safety factors are hidden deep inside the mechanism, buried in the math and the metal. One of the most important, and often overlooked, of these is the gear ratio. It is a simple number, but it has massive implications for how a robot moves, how it stops, what happens when things go wrong. You might think a robot is just a motor connected to a limb, but almost always, there is a gearbox in between. This collection of gears is the unsung hero of robotics, translating the motor's raw power into useful motion. However, this translation process fundamentally changes the robot's behavior. It can multiply force to incredible levels, or increase speed to a blur. Understanding this relationship is not just good engineering, it is a life-and-death safety consideration. A robot that cannot stop when you tell it to, or one that stops with the force of a hydraulic press, is a disaster waiting to happen. The gear ratio is the key that unlocks this behavior. So, what is this magic number? At its core, a gear ratio is beautifully simple. It is a comparison. It compares the rotation of the input gear, which is connected to the motor, to the rotation of the output gear, which is connected to the robot's joint or wheel. If the motor has to spin its little gear 10 times to make the big output gear turn just once, we have a 10-to-1 gear ratio. We call this a gear reduction because we are reducing the output speed. It is the same concept that lets you pedal a bicycle up a steep hill. Imagine two gears meshed together. One is small, with 10 teeth, and it is being spun by your motor. The other is large, with 100 teeth, and it is attached to the robot's arm. The small gear must turn 10 times for the big gear to turn once. Voila! 10-to-1. The output is 10 times slower than the input. It is a direct, physical relationship you can see and count, but here is where the magic and the danger comes in. This trade-off is not just about speed, it also affects torque, the rotational force. Reduce speed by 10, and you multiply torque by about 10, minus some losses. That little motor can now exert 10 times its turning force. A high ratio like 100-to-1 gives immense torque and precise slow control, great for heavy or delicate tasks. A low ratio like 2-to-1 gives higher speed with less torque. The ratio defines whether your robot is a powerlifter or a sprinter, and this choice drives how it will stop. Now we get to the heart of the safety problem: stopping. In a perfect world, an emergency stop would freeze everything, but physics, inertia, says otherwise. Inertia is an object's resistance to a change in motion. A heavy robot arm swinging at high speed has a lot of inertia. It will not stop on a dime. The gear ratio you choose massively affects that inertia, and it changes the robot's stopping distance. Consider a 100-to-1 gear ratio. It makes the arm slow and gives huge torque. It multiplies the motor's inertia by the square of the ratio, 10,000, creating tremendous rotational inertia at the joint. Trigger-safe torque. Off and you cut power to the motor. You are not applying a brake. You are letting the system coast. With reflected inertia that big, the coast can be very long. That is why standards like ANSI RAE R15.06 matter. The standard requires a risk assessment. You must figure stopping time and stopping distance for every hazardous motion. You cannot just guess, measure, or calculate it under real-world payload. If a high-gear robot takes too long to stop, a worker who thinks they are safe might not be. The safe zone could be inside the coast zone. Safe limited speed can be tricky. The speed may be low, but torque can remain enormous. A worker pinned at a safe speed but with hydraulic ram force faces the same outcome. Your risk assessment must account for both speed and force. Gear ratio is the link. Think beyond speed. Consider the crushing hazard. Let us make this real with a couple of examples from the field. First, picture a palletizing robot. Its job is to lift heavy boxes and stack them onto a pallet. You need a lot of torque, so designers choose a high gear ratio, maybe 80-to-1. The arm moves in a large, sweeping arc. The ANSI/RIAR 15.06 standard tells us this is a hazard. During the risk assessment, the team calculates consequences. If the power is cut mid-swing using STO, the arm will coast for nearly 2 feet. This is an unacceptable risk. The solution is not to rely only on the motor's safety function. Because of the high gear ratio and the payload, the risk of the load falling or coasting is too great. The correct engineering control is a mechanical brake, often spring-applied, power-released, that clamps the joint and holds position on power loss. The risk assessment document would explicitly call out this requirement. Now, a small SCARA for electronics. It needs to be fast and nimble, not powerful, using a low ratio like 10:1 or even direct drive. Here the primary hazard is high-speed impact. STO might work quickly because inertia is low, but speed is still the problem. ANSI/RIAR 15.06 guides solutions like light curtains or area scanners, creating invisible barriers. So, we have seen how a single number, the gear ratio, can ripple through an entire robotic system and create serious safety hazards. It is not just a performance spec, it is a safety spec. Taming this beast requires a systematic approach, not guesswork. Building a culture of safety from the beginning, respecting the power you unleash and putting the right controls in place. Here is your checklist. First, consciously choose your gear ratio. Do not just pick one that seems good enough. Analyze the task. Do you need high torque or high speed? Calculate the forces involved, then immediately analyze the safety implications. High ratio means plan for increased inertia and stopping distance. Low ratio means focus on impact energy and fast-acting protective devices. Document this decision in your design files. Second, test. Build the real thing and test worst case. Load the maximum payload, run maximum speed, trigger stops, and measure time and distance. Use certified components and verify STO, SLS and every safety function. Third, follow a recognized standard like ANSI RIAR 15.06. Identify hazards, assess risks, implement and validate controls, and treat gear ratio as a major input.